The universe stretches out in every direction, a vast and breathtaking tapestry of mysteries waiting to be uncovered. But hidden within that infinite expanse are places so extreme, they defy everything we know about reality, environments where the laws of physics twist into something unrecognizable, where temperatures soar beyond imagination, and where gravity itself bends to unfathomable forces. Picture a world where a single teaspoon of material weighs as much as a mountain, or a void so dark and dense that not even light can escape its grasp. These aren't scenes from science fiction, they're real, and they're out there, lurking in the cosmic shadows, pushing the very boundaries of what we thought possible. From the crushing depths of black holes to the searing fury of neutron stars, the universe is filled with realms that challenge our understanding of existence. Imagine wandering planets adrift in the void, untethered from any star, drifting through eternal night. Or consider magnetars, stellar corpses with magnetic fields so powerful they could strip the data from every credit card on Earth from halfway across the galaxy. These aren't just distant curiosities, they're the ultimate laboratories of nature, testing the limits of matter, energy, and time itself. And yet, for all their violence and extremes, they hold secrets, clues about how the cosmos was born, how it evolves, and perhaps even how it might one day end. This journey isn't just about cataloging the universe's most hostile corners, it's about uncovering the stories they tell. Every extreme environment is a puzzle piece in the grand mystery of existence, a place where the rules we take for granted no longer apply. And as we explore these realms, from the heart of supermassive black holes to the frozen wastelands of rogue planets, we'll discover just how strange, how beautiful, and how utterly unpredictable the universe truly is. So buckle up, because what lies ahead will stretch your imagination, challenge your perceptions, and leave you in awe of the cosmic wonders that lurk beyond the stars. The core of a neutron star is one of the most extreme places in the universe, a place where matter doesn't just bend the rules, it smashes them to pieces. Picture this: a single sugar cube-sized chunk of neutron star material would weigh a staggering 1 billion tons here on Earth. That's like taking an entire mountain range, rock, ice, and all, and crushing it down until it fits in your morning coffee. How is that even possible? It all comes down to gravity's merciless grip. When a massive star runs out of fuel and collapses, the sheer force of its own weight crushes atoms beyond recognition. Protons and electrons, normally content to orbit each other at a safe distance, get squeezed together until they merge into neutrons. The result, a solid ball of nuclear matter so dense, a single teaspoon of it would outweigh every car, building, and skyscraper on our planet combined. But here's where it gets even stranger. This isn't just dense, it's matter in a state that defies ordinary physics. Under normal conditions, atoms are mostly empty space, with electrons whizzing far from their nuclei. But in a neutron star's core, that emptiness vanishes. Every bit of space gets packed with neutrons, shoulder to shoulder, like an endless sea of subatomic marbles with no gaps between them. If you could somehow scoop up a piece and bring it to Earth, it wouldn't just be heavy, it would be indestructible, resisting any force trying to pull it apart. The gravity alone would punch straight through the floor, sinking deeper into the planet like a bullet through water. To put that density into perspective, imagine compressing Mount Everest into a teaspoon. That's not just shrinking it down, it's erasing every single pocket of air, every microscopic gap, until only pure, unbroken mass remains. And yet, neutron stars do this on a cosmic scale, cramming more than our entire sun's worth of material into a city-sized sphere. The universe has plenty of extreme environments, but few can match the sheer, terrifying density of a neutron star's heart, where the ordinary laws of matter surrender to something far more alien, far more unbelievable. If neutron stars are the universe's ultimate heavyweights, then magnetars are their terrifying, ultra-magnetized cousins, cosmic monsters where magnetic forces reach almost unimaginable extremes. These aren't just strong magnets, they're nature's most destructive force fields with a grip so powerful it can tear atoms apart from thousands of miles away. To put that in perspective, a typical fridge magnet might lift a paperclip, but a magnetar's field, it could rip the iron right out of your blood from halfway across the solar system. The numbers alone are staggering. Earth's magnetic field is gentle enough to guide compass needles measuring about 1 Gauss, a magnetar's field a quadrillion times stronger. That's a 1 followed by 15 zeros, an intensity so extreme, it warps the very fabric of space-time around it. At close range, the magnetic forces twist atoms into impossibly thin, needle-like shapes, stripping away electrons and leaving behind a bizarre, ionized plasma that shouldn't exist anywhere else in the universe. But the chaos doesn't stop there. Magnetars are also prone to violent tantrums known as starquakes. Like earthquakes, but infinitely more destructive, these cosmic tremors happen when the star's rigid crust, already under unimaginable strain, suddenly cracks under the pressure. When that happens, the energy released is mind-blowing. Gamma-ray flares so bright they outshine entire galaxies for a fraction of a second. In 2004, a magnetar 50,000 light-years away fired off a burst so powerful it temporarily ionized Earth's upper atmosphere, even from that staggering distance. What makes these outbursts even more unsettling is their unpredictability. Unlike pulsars, which spin with clockwork precision, magnetars are erratic, their magnetic fields so unstable they can flip polarity in seconds. One moment they're silent, the next they're hurling enough energy into space to wipe out any nearby planets. And yet, for all their fury, magnetars might hold the key to some of the universe's greatest mysteries, like the origins of fast radio bursts, those enigmatic cosmic signals that have puzzled astronomers for decades. So while we might never set foot near one of these magnetic nightmares, their existence forces us to rethink what's possible. In a universe full of extremes, magnetars stand apart, not just as destroyers, but as reminders of how little we truly understand about the forces that shape reality itself. At the edge of a black hole lies one of the most ominous boundaries in the universe, the event horizon, a point of no return where the laws of physics as we know them begin to unravel. Step beyond this invisible line, and not even light, the fastest thing in existence, can escape the gravitational grip. It's like crossing the threshold of a cosmic prison where the walls are made of pure space-time curvature, bending so severely that every possible path leads inward, deeper into the abyss. Approaching this boundary, a gruesome phenomenon awaits: spaghettification. The name might sound whimsical, but the reality is anything but. As an object nears a black hole, the difference in gravitational pull between its top and bottom becomes so extreme that it stretches like taffy, elongating into thin, noodle-like strands. Imagine your feet feeling a force exponentially stronger than your head within seconds. Every molecule in your body would be pulled apart in a grotesque, one-way transformation. Even stars aren't spared this fate. When they wander too close, they're shredded into luminous ribbons of plasma, swirling into the void like celestial spaghetti. But not all black holes are created equal. Stellar black holes, born from the collapse of massive stars, might span just a few miles across yet pack several times the sun's mass into that tiny space. Their event horizons are smaller but no less deadly, with tidal forces so intense they'd spaghettify you long before you reach them. Supermassive black holes, on the other hand, are the giants lurking at the centers of galaxies. With masses millions or even billions of times that of our sun, their event horizons stretch so wide you could cross them without even noticing at first. The gravity near these behemoths is spread over such vast distances that you'd glide past the point of no return smoothly, only realizing your doom as space-time itself folded irrevocably around you. What makes these cosmic predators even more fascinating is how they warp the very fabric of reality. Near the event horizon, time slows to a crawl. To a distant observer, a falling object would appear to freeze, fading into redshifted obscurity as the black hole's gravity stretches light into oblivion. Yet for the doomed traveler, time marches forward relentlessly, dragging them toward the singularity, a place where all known physics breaks down and the universe's darkest secrets might lie hidden. Black holes aren't just destroyers, they're the ultimate expression of gravity's power, bending space-time into knots and challenging everything we think we know about existence. Whether stellar or supermassive, they serve as stark reminders that the universe harbors realms where the ordinary rules don't just bend, they shatter completely. Deep within a black hole, beyond the event horizon, lies a place where reality itself collapses, the singularity. This is the heart of cosmic madness, where the laws of physics as we understand them cease to function. Imagine compressing all the mass of a star or even an entire galaxy into an infinitely tiny point, a place where density becomes so extreme that space and time lose all meaning. Here, gravity doesn't just bend the rules, it erases them entirely. At the singularity, the equations of general relativity break down, predicting infinite curvature and infinite gravity. But infinities don't exist in nature. They're a sign that our science has reached its limits. This is where Einstein's theory meets its greatest challenge, unable to reconcile with the bizarre quantum realm that governs the subatomic world. The singularity isn't just a point of extreme density, it's a cosmic question mark, a screaming void where our understanding of existence hits a wall. Yet even in this chaos there are clues. Stephen Hawking proposed that black holes aren't entirely black, they emit faint radiation, slowly leaking energy and evaporating over incomprehensible timescales. This Hawking radiation suggests that black holes might not be eternal prisons after all, but temporary phenomena that eventually fade into nothingness. But here's the catch: if Hawking radiation exists, what happens to all the information swallowed by the black hole? Quantum mechanics says information can't be destroyed, but black holes seem to erase it completely, a paradox that still divides physicists today. Then there's the firewall paradox, a mind-bending idea that the event horizon might not be as smooth as relativity predicts. Instead, it could be a raging inferno of high-energy particles, a lethal barrier that incinerates anything crossing it. If true, this would mean the peaceful descent into a black hole, as described by Einstein, is an illusion. Reality might be far more violent at the brink of oblivion. The singularity represents the ultimate frontier of human knowledge, a place where relativity and quantum mechanics clash in spectacular fashion. Some theories suggest singularities might not be points at all, but loops or rings, twisting space-time into bizarre new shapes. Others propose they could be gateways to entirely different universes. One thing's certain: until we crack the code of quantum gravity, the singularity will remain one of the universe's most profound mysteries, a cosmic glitch where the rulebook of reality tears at the seams. If you think scorching summer heat is unbearable, imagine a world where the oceans themselves are boiling not with water, but with vaporized rock. That's the nightmare reality of Kepler 70b, an exoplanet so hellishly hot it makes lava look like a refreshing dip. With surface temperatures soaring beyond 7,000 degrees Fahrenheit, this isn't just a hostile environment, it's a realm where the very concept of solid ground evaporates. Locked in a death spiral around its dying star, Kepler 70b completes an entire orbit in less than 6 hours, so close that tidal forces stretch and knead the planet like molten dough. The gravitational tug is so intense it keeps the planet's surface perpetually churning, a bubbling cauldron of superheated rock vapor. Picture standing on this world, except there's no standing. The ground beneath your feet would be a seething ocean of silicate steam, surges of liquefied minerals rising and collapsing in waves hundreds of miles high. Even the sky is apocalyptic, glowing crimson from the relentless radiation of its aging host star, which scorches the planet with ultraviolet fury. What makes Kepler 70b even more bizarre is its origin story. Once a gas giant like Jupiter, its atmosphere was stripped away by the star's wrath, leaving behind a naked, superheated core. Now, it's essentially a planetary skeleton, its rocky remains caught in a gravitational vice, melting and churning under forces we can scarcely comprehend. Astronomers call these worlds ultra-short-period planets, but that clinical term hardly captures the violence of their existence. Yet for all its fury, Kepler 70b isn't alone. The universe is full of these tortured worlds, extreme examples of what happens when a planet strays too close to its star's wrath. They're cosmic laboratories showing us just how far planetary environments can be pushed and how strange the universe gets when the rules we take for granted no longer apply. Forget raindrops on Neptune and Uranus, the skies literally rain diamonds. This isn't science fiction. It's the bizarre reality of chemistry under crushing pressure, where methane, the same gas that fuels stoves on Earth, transforms into glittering gemstones. Picture this: deep in the swirling, blue-hued atmospheres of these ice giants, violent storms churn methane molecules, breaking them apart under pressures hundreds of thousands of times stronger than Earth's surface. The carbon atoms, stripped from their hydrogen companions, get squeezed so tightly they lock into crystalline structures, raw diamonds, forged in the planet's turbulent skies. But the spectacle doesn't stop there. These diamonds don't gently float down, they plummet like hailstones, superheated and accelerated by the planet's fierce gravity. Some could grow as large as icebergs, colliding and fracturing in the dense atmosphere, and the deeper they sink, the stranger it gets. Scientists theorize that far below the cloud layers, these diamonds might collect into vast, floating bergs atop oceans of liquid carbon. Imagine a sea so dark and dense it makes Earth's oceans look like puddles, with diamond mountains bobbing like surreal, glittering islands. The process behind this cosmic jewelry show starts with methane, abundant in both planets' upper atmospheres. When lightning strikes or extreme pressures take hold, the methane shatters, releasing carbon atoms that bond under the intense squeeze. Laboratory experiments on Earth have recreated these conditions, zapping hydrocarbons with lasers to mimic the planet's interiors, confirming that yes, diamonds really can form this way. What makes this phenomenon even wilder is the scale. On Uranus and Neptune, diamond rain isn't occasional, it's constant, a never-ending storm of riches that would bankrupt every gem dealer on Earth. But here's the cruel twist: even if we could reach these diamond hailstones, they'd be impossible to retrieve. The pressures and temperatures are so extreme, they'd vaporize any spacecraft long before it could grab a sample. Neptune and Uranus remind us that the universe's most astonishing treasures often exist in its most inhospitable corners. Diamond rain isn't just a curiosity, it's proof that under the right conditions, even the simplest elements can become something extraordinary. And while we might never mine these alien gemstones, their existence challenges everything we thought we knew about how matter behaves when pushed to the limit. Some stars don't just drift through the cosmos, they're hurled into the void like cosmic bullets, racing at speeds so extreme they could cross the length of Earth in less than a second. These are hypervelocity stars, stellar fugitives flung from their homes with such force that they're destined to abandon their galaxies forever, and the culprit behind this interstellar exile. A supermassive black hole's gravitational slingshot, a cosmic game of pinball where the stakes are nothing less than escape velocity on a galactic scale. Picture a binary star system, two stars orbiting each other, wandering too close to the monster lurking at a galaxy's center. The black hole's gravity seizes one star, dragging it into a lethal orbit while its companion gets catapulted outward at mind-blowing speeds. We're talking millions of miles per hour, so fast that these stars don't just leave their neighborhoods behind, they blaze through space with enough energy to eventually break free from the Milky Way's grip entirely. Some have already been clocked at speeds exceeding 1.5 million miles per hour, streaking toward intergalactic space like lone wanderers in an endless dark. What makes these stars even more fascinating are the scars they leave behind. As they tear through clouds of interstellar gas at breakneck speeds, they create shockwaves, visible trails of superheated plasma glowing in their wake. It's like watching a speedboat rip across a cosmic lake, leaving a rippling, luminous disturbance in the void. Astronomers can actually track these paths, using them to trace the stars' frantic journeys back to their violent origins near black holes. But where do they go once they're ejected? Some might drift forever through the emptiness between galaxies, their light fading into obscurity. Others could someday collide with another galaxy, though that encounter would take billions of years. And in rare cases, a hypervelocity star might pass close enough to another system to disrupt planets or even get captured, though by then its speed would have dwindled from its initial explosive ejection. Hypervelocity stars are more than just celestial oddities. They're proof of the chaos lurking at the hearts of galaxies, where black holes don't just consume matter, but fling it into the void with unimaginable force. They remind us that even in the vastness of space, nothing is truly stationary, and that the universe has a way of turning gravity into both a prison and a catapult. Between galaxies, space isn't just empty, it's a void so vast and desolate, it makes the vacuum of our solar system seem crowded by comparison. Out there, in the unimaginable stretches of intergalactic space, a single cubic meter might hold just one solitary atom. To put that in perspective, every breath you take on Earth contains more air molecules than there are stars in the entire Milky Way. It's the closest thing to true nothingness the universe has to offer, a silent, freezing desert stretching billions of light years in every direction. Imagine standing in this cosmic wasteland. There's no wind, no sound, no warmth, just an endless, crushing absence. The temperature hovers just a few degrees above absolute zero, cold enough to freeze atoms into near stillness. Without the protective cocoon of Earth's atmosphere, the vacuum would pull the air from your lungs in seconds, while your body's fluids would boil away into the void. And yet, for all its emptiness, this space isn't completely barren. Those sparse, drifting atoms, mostly hydrogen, remnants of the Big Bang, are the raw materials of future galaxies, the faint echoes of a time when the universe was young and crowded with possibility. The sheer scale of this emptiness defies comprehension. If Earth's atmosphere were as thin as intergalactic space, it wouldn't stretch to the top of a skyscraper. It would barely cover a single step. That's how extreme the contrast is. Even between stars within our own galaxy, space is relatively dense, like a few grains of sand scattered across a football field. But between galaxies, it's more like a single grain lost in an ocean. Yet, paradoxically, these unimaginable voids are what make the universe navigable. Without such vast emptiness, gravity's pull would tangle galaxies into constant collisions. Stars would burn too hot from cosmic debris, and life as we know it might never have had the chance to emerge. This perfect vacuum is nature's way of keeping the cosmos orderly, a blank canvas where galaxies can drift apart, preserving the delicate balance that allows everything else to exist. So while intergalactic space might seem like the universe's most lonesome corner, it's also one of its most essential. Without these impossibly empty stretches, the glittering islands of stars we call galaxies wouldn't shine so brightly or exist at all. It's a reminder that sometimes nothingness isn't just absence, it's the foundation for everything else. Venus might be Earth's twin in size, but its atmosphere is a nightmare straight out of science fiction, a suffocating, superheated hellscape where even metal melts like butter. At 900 degrees Fahrenheit, the surface is hot enough to vaporize lead, turning what should be a rocky world into a pressure cooker from hell. And the heat isn't the only killer. The air itself crushes down with 90 times the pressure of Earth's, as if you were submerged a mile deep in the ocean, except instead of water, it's a toxic soup of carbon dioxide and sulfuric acid. This is the runaway greenhouse effect taken to its most extreme conclusion. Sunlight punches through Venus's thick cloud cover, but once it heats the surface, the energy can't escape. Trapped by the dense carbon dioxide atmosphere, temperatures soar until rocks glow red-hot and the very air becomes a furnace. Those ominous yellow clouds aren't made of water vapor. They're sulfuric acid, corrosive enough to eat through spacecraft plating in seconds. It's a planet where rain doesn't bring relief. It burns like battery acid before evaporating long before reaching the ground. The Soviets learned just how hostile Venus truly is when they sent their Venera probes in the 1970s. These sturdy machines, built to withstand extremes, barely lasted minutes before succumbing to the planet's wrath. Venera 13, the most resilient of them all, transmitted data for just 127 minutes before its electronics fried and its hull crumpled under the unbearable pressure. Even its cameras, designed to snap quick panoramas, captured only hazy, orange-tinted glimpses of a desolate wasteland littered with cracked bedrock. The last things a human would see before being crushed, roasted, and dissolved all at once. What makes Venus's horror show even more unsettling is how close it came to being habitable. Billions of years ago, it might have had oceans, temperate climates, even conditions ripe for life. But a tipping point was crossed, perhaps from volcanic activity spewing too much CO2 or the sun's gradual brightening, and the planet spiraled into oblivion. Now it stands as a grim warning of what happens when a greenhouse effect runs unchecked, a vision of Earth's potential future if climate boundaries are pushed too far. Yet for all its lethality, Venus fascinates scientists. Its thick atmosphere acts like a planetary lab, showcasing how gases can warp a world beyond recognition. And hidden in its acid clouds, some speculate, could be microbial life organisms tough enough to survive in droplets far above the scorching surface. Whether a cautionary tale or a puzzle waiting to be solved, Venus proves one thing. In the cosmos, even paradise can turn to hell. Beneath the frozen crust of Jupiter's moon Europa lies an ocean, not of water as we know it, but a vast globe-spanning sea trapped under miles of ice. And just like Earth's restless volcanoes, Europa has its own version of eruptions, cryovolcanos, where plumes of icy water and gas blast into space from cracks in the moon's shimmering surface. These aren't fiery explosions of molten rock, but slow, eerie fountains of slush and vapor, some reaching hundreds of miles high before freezing into glittering spaceborne frost. What powers these otherworldly eruptions? The answer lies in the tremendous tidal forces Jupiter exerts on its tiny moon. As Europa orbits, the gas giant's gravity stretches and compresses its core, generating enough internal heat to keep the subsurface ocean liquid. That same friction cracks the icy shell, creating pathways for water to escape, sometimes gently seeping, sometimes erupting in spectacular jets. Scientists have spotted these plumes multiple times, even detecting water vapor in their spectral signatures, a tantalizing hint of the hidden ocean below. But here's where it gets thrilling. On Earth, hydrothermal vents, blazing hot springs on the ocean floor, teem with life, thriving without sunlight in conditions once thought uninhabitable. Europa's cryovolcanos could be offering similar oases. If nutrients and heat from the moon's rocky core mix with liquid water at these vents, the stage could be set for extraterrestrial microbes. The chemistry is plausible. Europa's ocean likely contains salts and organic molecules stirred by tidal energy. It wouldn't take much, just the right combination of warmth, chemistry, and time, for life to cling to these underwater chimneys, feeding off the moon's hidden energy. The parallels with Earth's extremes are uncanny. In the pitch-black depths of our own oceans, entire ecosystems thrive around volcanic vents, fueled by chemosynthesis rather than sunlight. Europa's cryovolcanic plumes might be sampling that alien ocean, spraying its contents into space where missions like NASA Europa Clipper could one day analyze them. A single flyby through one of these jets might reveal organic compounds or even microbial life hitching a ride on icy particles. For now, Europa remains a world of mystery, its geysers both a beacon and a puzzle. They remind us that life doesn't need sunny shores or open skies, just liquid, energy, and the right ingredients. And if something is stirring in those dark, salty depths, it would redefine our place in the cosmos. After all, a moon barely the size of our own could be hiding the second genesis of life in the solar system, not in some distant star system, but right in our own celestial backyard. The sun might look like a peaceful golden orb from Earth, but its surface is a raging battlefield of plasma storms, explosions of energy so violent they dwarf every nuclear weapon ever built combined. At the heart of these eruptions are solar flares and coronal mass ejections, where temperatures rocket past tens of millions of degrees, turning gas into a supercharged inferno of electrically charged particles. These aren't just bursts of heat, they're titanic eruptions of magnetic energy, twisting and snapping like cosmic rubber bands until they unleash enough power to light up civilizations for millennia. A single solar flare can release the energy of 1 billion hydrogen bombs in mere minutes, blasting radiation across the solar system at nearly the speed of light. But the real showstoppers are coronal mass ejections, billion-ton clouds of magnetized plasma hurled into space like celestial cannon fire. When one of these monsters slams into Earth's magnetic field, it doesn't just create the shimmering auroras we admire. It also has the power to cripple satellites, knock out power grids, and scramble GPS signals, sending modern technology back to the Stone Age in hours. Back in 1859, the largest recorded solar storm, the Carrington event, lit up telegraph lines so intensely that operators got electrocuted by their own equipment. Skies turned crimson as far south as the Caribbean, and if a storm like that hit today, experts estimate it could trigger blackouts lasting months, with damages soaring into the trillions. Even smaller solar tantrums cause havoc. In 1989, a geomagnetic storm fried transformers in Quebec, plunging millions into darkness in seconds. Satellites aren't safe either. Their delicate electronics get bombarded by high-energy particles, slowly degrading until they become expensive space junk. But these plasma storms aren't just agents of chaos. They're also sculptors of cosmic beauty. When solar wind particles spiral down Earth's magnetic field lines, they collide with atmospheric gases, igniting the ethereal glow of the auroras. Oxygen burns green, nitrogen flares red and purple, nature's own celestial light show dancing over polar skies. The same forces that threaten our tech also paint the heavens with otherworldly colors, proving that even the universe's most destructive powers can create something breathtaking. Understanding these solar outbursts isn't just about protecting our gadgets, it's about decoding the sun's volatile personality. Missions like NASA's Parker solar probe dive perilously close to the sun's corona, braving temperatures hot enough to vaporize steel just to unravel the secrets behind these storms. Because in the end, the sun doesn't just give us light and warmth, it's a constant reminder that our star is both life-giver and potential disruptor, capable of painting the sky with magic or plunging us into darkness with a single, furious breath. On Saturn's largest moon, Titan, the familiar gives way to the bizarre, a world where rivers carve valleys not with water, but with liquid methane, where icy shores meet hydrocarbon waves under an orange haze thick enough to blot out the stars. This isn't a dystopian fantasy. It's the only place in the solar system besides Earth with active liquid flowing across its surface. But forget tropical beaches or babbling brooks. Titan's landscape is a cryogenic nightmare, with temperatures plunging to negative 290 degrees Fahrenheit, so cold that water turns to rock-hard ice, and methane takes on the role Earth reserves for water, falling as rain, pooling into lakes, and even carving canyons over millennia. The sheer strangeness begins with Titan's atmosphere, a dense, nitrogen-rich shroud laced with organic compounds, Sunlight filtering through this orange smog triggers chemical reactions that produce ethane and methane, which then condense into clouds and fall as oily droplets. When these hydrocarbons hit the ground, they behave almost like water on Earth, except everything's in grotesque slow motion. Methane's viscosity is lower than water's, so it flows more like gasoline, cascading in sluggish rivulets across ice cliffs and gathering in vast, glassy lakes near the poles. Some of these methane seas stretch hundreds of miles across, deeper than the Great Lakes, their surfaces so still they reflect Titan's hazy sky like dark mirrors. But the real shocker, Titan has a full liquid cycle mirroring Earth's hydrologic system, just swapped with chemicals that would suffocate and freeze us in an instant. Methane evaporates from lakes, forms clouds, and rains back down, eroding the water-ice bedrock into jagged ridges and valleys. Wind sculpts the damp hydrocarbon sands into dunes as tall as skyscrapers, marching across equatorial deserts in waves that look eerily like those in Namibia, except these dunes are made of plastic-like particles, a gritty mix of organic sludge and ice grains. Then there's the surreal shoreline of Kraken Mare, Titan's largest methane sea. Radar images from NASA Cassini probe revealed coastlines etched with inlets and bays, suggesting tidal forces at work. But without moon-sized waves, the liquid here slides rather than crashes, lapping at icy headlands with the gentleness of oil spilling across a tabletop. Beneath that surface, some scientists speculate, could lie layers of exotic slush acetylene or benzene mixed with methane, or even pockets of nitrogen bubbling up from below like fizzy soda. What makes Titan's methane lakes more than just a cosmic curiosity is what they imply about life's possibilities. In Titan's cryogenic chemistry, methane plays the role water does on Earth: a solvent, a mover of molecules, a medium for reactions. Some astrobiologists theorize that life could exist here, not as we know it, but as methane-based organisms breathing hydrogen instead of oxygen, their cells built from hydrocarbons floating in those frigid seas. It's a stretch, but not impossible. After all, Earth's extremophiles thrive in boiling vents and acidic pools. Why not creatures adapted to liquid methane and perpetual cold? Titan challenges every assumption about what makes a world habitable or dynamic. It's a looking-glass version of Earth, where familiar processes unfold with alien ingredients, proving that the universe's creativity doesn't just mimic our home, it reinvents it entirely. And as future missions like Dragonfly prepare to soar through Titan's thick air, we might soon discover whether this moon's eerie landscapes are merely geologic wonders or something far more extraordinary. Somewhere in the pitch-black vastness between stars, a rogue planet drifts untethered from any sun, lost in the eternal freeze of interstellar space. This isn't just a wandering rock, it's a world without a dawn where the concept of daytime doesn't exist and temperatures hover just a whisper above absolute zero. Yet beneath its frozen crust, something astonishing might lurk, a hidden ocean kept liquid not by sunlight, but by the slow, relentless heartbeat of radioactive decay deep in the planet's core. Imagine a world where geothermal heat replaces sunlight. Without a star to warm it, a rogue planet's only warmth comes from the radioactive elements simmering in its core: uranium, thorium, potassium, their particles colliding and releasing energy over billions of years. This decay generates just enough heat to melt deep reservoirs of ice, creating subsurface oceans sealed under miles of glacier-like crust. It's like a cosmic thermos, trapping warmth in the darkness, where pressures keep the water liquid even in unimaginable cold. Here's where it gets even more intriguing. On Earth, life thrives in the most unexpected places: bacteria flourishing in boiling hydrothermal vents, microbes surviving in Antarctic ice. Could similar extremophiles exist in these lightless alien oceans? The chemistry is plausible. Hydrothermal vents on rogue planets might bubble with mineral-rich fluids, offering energy sources for organisms that don't rely on photosynthesis. Instead of sunlight, they'd harvest chemical energy, much like the creatures in Earth's deepest, darkest trenches. Some scientists speculate these oceans could even host complex ecosystems, their existence hidden beneath armor-thick ice, shielded from the deadly void above. The odds of such life might seem slim, but rogue planets are shockingly common. Astronomers estimate there could be billions drifting through our galaxy alone, dark, silent worlds ejected from their birth systems by gravitational chaos. Some might even pass relatively close to us, undetectable because they emit no light. If life could cling to these frozen outcasts, it would redefine our understanding of habitability. After all, planets don't need to orbit stars to harbor life, they just need the right internal fire. What's truly humbling is the resilience of these forgotten worlds. Without sunsets or seasons, they float in perpetual night, their oceans, if they exist, stirring in slow, unseen currents. They're proof that the universe doesn't need warmth or light to craft environments teeming with possibility, just time, chemistry, and the faint, enduring glow of radioactive decay. And if life does lurk in those abysses, it would mean the cosmos is far stranger and far more tenacious than we ever dared dream. At the centers of some of the universe's most ancient galaxies, cosmic monsters lurk, supermassive black holes so insatiable they don't just consume matter, they blast the leftovers into space with enough force to outshine entire galaxies. These are quasars, nature's ultimate particle accelerators, spewing jets of superheated plasma at nearly the speed of light across millions of light years. Imagine a beam of energy so intense it could vaporize every planet in our solar system in seconds, and then multiply that by 1 trillion. That's the raw power of a quasar's jet, a lighthouse of destruction visible clear across the observable universe. What makes these beams even more astonishing is their sheer luminosity. At their peak, quasars can shine with the brightness of 1 trillion suns, more than all the stars in our Milky Way combined. Some are so mind-bendingly powerful, we can still detect them from over 12 billion light-years away, their light just now reaching us from the universe's fiery infancy. To put that in perspective, when the light from these quasars began its journey, Earth didn't even exist, and the cosmos was still clumping together its first galaxies. The violence begins deep within the quasar's accretion disk, a swirling maelstrom of gas, dust, and shredded stars spiraling toward the black hole's event horizon. But not all that material gets swallowed. Intense magnetic fields, twisted by the black hole's insane rotation, funnel some of it outward along the poles, accelerating particles to near-light speeds. The result, twin jets of plasma erupting like cosmic fire hoses, stretching hundreds of thousands of light years into intergalactic space. These aren't gentle streams, they're tsunamis of raw energy, packing enough punch to reshape entire galaxies in their path. One of the most extreme examples lies in the constellation Virgo, Quasar 3C273. Its jet stretches a mind-numbing 1.5 million light-years, 15 times the diameter of our Milky Way. Even more bizarre, the jet isn't straight. It corkscrews through space like a writhing serpent, its path warped by the black hole's spin and the turbulent gas it plows through. But quasars aren't just destructive. Their beams inject energy into the cosmos like cosmic fertilizer, heating surrounding gas and triggering or stifling star formation in their host galaxies. Some scientists even speculate that quasar jets could be the universe's way of redistributing matter, seeding future generations of stars and planets with heavy elements forged in their fiery wakes. Ultimately, quasars are a paradox, both annihilators and creators, their fury shaping the cosmos as much as their light illuminates it. They remind us that even the darkest hearts of galaxies can unleash some of the most dazzling spectacles in existence, beacons from the dawn of time, burning bright against the infinite night. Jupiter's moon, Io, is a world of fire and chaos, where the ground itself breathes with the fury of hundreds of active volcanoes. Unlike Earth's occasional eruptions, Io's surface is a constant battleground, ripped apart by tidal forces so intense they turn the moon's interior into a bubbling cauldron of molten rock. Picture a place where lava fountains shoot dozens of miles into the thin, sulfurous sky, where rivers of liquid rock carve fresh scars across the landscape every single day. This isn't just geological activity, it's a full-scale planetary revolt, a moon fighting against the brutal gravitational grip of its parent planet. The violence begins with Jupiter's relentless pull. As Io orbits, the gas giant's gravity yanks and stretches the moon like taffy, its rocky crust flexing and groaning under the strain. This tidal heating generates so much friction inside Io that its core melts, fueling volcanic eruptions hundreds of times more powerful than anything on Earth. Some of these outbursts are so colossal, they've been spotted by telescopes from over 400 million miles away, spewing plumes of sulfur and sulfur dioxide high enough to escape Io's weak gravity and paint its orbit with a faint, ghostly ring. What makes Io's eruptions truly surreal is their aftermath. The ejected sulfur doesn't just fall back as ash, it blankets the surface in vivid splashes of color-fiery reds, neon yellows, and electric greens, all swirled together like a cosmic oil slick. These aren't static landscapes. The sulfur compounds shift and change over time, reacting with radiation and fresh eruptions to create ever-shifting kaleidoscopes of chemical chaos. Some regions look like they've been spray-painted by an erratic artist, while others resemble burnt marshmallows, their crusts cracked and oozing molten material from below. But the real spectacle lies in Io's lava lakes. Unlike Earth's basaltic flows, these are seas of ultra-hot silicate lava, so fluid they behave like water, constantly churning and bubbling. The largest, Loki Patera, stretches over 100 miles wide, a roiling, blackened cauldron with a thin crust that cracks and refreezes in an endless cycle. When the crust collapses, it triggers eruptions visible from space, bright flares of infrared energy signaling another violent reset. Io's eruptions don't just reshape its own surface, they feed Jupiter's magnetosphere with charged particles, creating a donut-shaped zone of radiation so intense it would fry unshielded electronics in seconds. Yet despite this hellish environment, Io teaches us how powerful tidal forces can sculpt worlds in ways we once thought impossible. It's a laboratory for extreme volcanism, proving that even without sunlight or plate tectonics, a moon can burn brighter than any planet, a flaming testament to gravity's creative and destructive might. Far beyond the orbits of Neptune and Pluto lies a vast, silent frontier, the Oort cloud, a spherical shell of icy relics stretching nearly halfway to the next star. This is no ordinary asteroid belt. It's a deep freeze archive of the solar system's raw materials, a graveyard of frozen leftovers from the chaotic construction site our cosmic neighborhood once was. Picture trillions of icy bodies, comets mostly, some as large as mountains drifting in perpetual twilight, so far from the sun that its light takes weeks to reach them. A single orbit here isn't measured in years, but in millennia, with some comets taking tens of millions of years to complete one sluggish lap around our star. What makes the Oort cloud so fascinating is its role as a cosmic catapult. Every so often, the gentle tug of a passing star or the ripple of galactic gravity nudges one of these dormant ice balls, sending it spiraling inward on a death dive toward the inner solar system. As it approaches the sun, heat vaporizes its frozen gases, transforming it into the blazing spectacle we recognize as a comet, a sudden streak of light with a shimmering tail stretching millions of miles. The very comets that have awed humanity for centuries, Halley's, Hale-Bopp, Ison, likely began their journeys in this distant frosty reservoir flung toward us by gravitational chance. Yet for all its importance, we've never seen the Oort cloud directly. Its objects are too small, too dark, and too far away for even our most powerful telescopes to spot. Instead, we infer its existence from the orbits of long-period comets, those rare wanderers that arrive from every direction, not just the flat plane of the solar system. These icy messengers are the only clues we have to this hidden realm, each one a time capsule holding ices and dust unchanged since the dawn of our planetary neighborhood. Imagine standing on one of these primordial icebergs. The sun would be just another faint star in a sea of darkness, its warmth too weak to melt even the surface frost. Out here, temperatures hover near absolute zero, cold enough to freeze nitrogen solid. And yet, within these frozen shells may lie the ingredients for life: water, organic molecules, even amino acids, the same building blocks that might have seeded Earth's oceans billions of years ago via similar comet strikes. The Oort cloud isn't just a museum of the past, it's a cosmic delivery service, occasionally sending parcels of ancient chemistry hurtling toward the inner planets where they could spark new beginnings. This distant swarm also serves as a stark reminder of how small our corner of space truly is. The Oort cloud marks the true boundary of the Sun's gravitational influence, the final frontier before interstellar space begins. Its outermost edges brush against the currents of the Milky Way, where the pull of other stars starts to compete with our own. One day, far in the future, many of these icy nomads will be stripped away entirely, lost to the galaxy's tides, a slow dispersal of the solar system's outermost fragments into the great dark beyond. For now, though, the Oort cloud remains the solar system's silent sentinel, a frozen vault holding secrets from our origins and perhaps the seeds of our future. Every comet that lights up our sky is a fleeting visitor from this uncharted territory, a reminder that even in the deepest cold, the universe keeps its mysteries on a long, celestial leash. Jupiter's radiation belts are the most violent in the solar system, a swirling hellscape of charged particles trapped in the gas giant's monstrous magnetic field. Imagine Earth's Van Allen belts but cranked to 1,000. Electrons and protons whip around at nearly the speed of light, packing enough energy to fry spacecraft circuits in hours and penetrate human tissue like microscopic bullets. This isn't just radiation, it's a particle accelerator the size of a planet, where forces so extreme they defy earthly logic turn the space around Jupiter into a death zone for anything unprepared. The sheer scale of Jupiter's magnetic grip is staggering. Its field stretches over 4 million miles into space, strong enough to tug on Saturn's orbit from hundreds of millions of miles away. At its core, electrons get catapulted to relativistic speeds, spiraling along magnetic field lines until they collide with moons, dust, or anything else unlucky enough to cross their path. The result, a donut-shaped kill zone around Jupiter's equator, with radiation levels millions of times stronger than what Earth's belts produce. Even NASA's sturdiest probes, like Juno, had to armor themselves in titanium shielding just to survive short flybys, and still, their cameras and sensors took gradual, irreparable damage from the onslaught. But the real nightmare is Io. The volcanic moon spews sulfur dioxide into space, where Jupiter's magnetic field ionizes it, creating a secondary ring of high-energy plasma. This Io plasma torus acts like a battery, constantly recharging the radiation belts with fresh particles. Every eruption on Io feeds the beast, adding fuel to a cycle that makes Jupiter's environment even deadlier. The radiation here is so intense, it strips atoms bare of their electrons, creating a soup of naked nuclei and supercharged particles that glow faintly in ultraviolet, a ghostly halo visible only to satellites brave enough to get close. Surviving this environment requires more than just thick metal. Engineers design spacecraft with redundant systems, burying critical electronics deep inside layers of shielding, and even then, missions must limit their exposure. Galileo, which orbited Jupiter for 8 years, saw its memory degrade and instruments fail one by one as radiation chewed through its defenses. Future missions like Europa Clipper will use elliptical orbits to dart in, gather data, and retreat before the radiation cooks their insides. Yet for all its lethality, Jupiter's radiation belts hold secrets about how planetary magnetic fields shape their environments. They're natural laboratories for studying particle acceleration, cosmic rays, and even the potential for life on ice moons like Europa, where the belts may indirectly provide energy by irradiating surface ice into oxygen. Jupiter reminds us that the universe doesn't just harbor beauty, it wields forces beyond our wildest reckoning, where even the void between worlds can become a storm of invisible fire. Deep within the heart of certain neutron stars, matter doesn't just behave strangely, it violates everything we know about how liquids should act. These ultra-dense remnants of dead stars may harbor cores of superfluid neutrons, a state where particles flow with zero friction, defying the very concept of viscosity. Picture an ocean where whirlpools never slow down, where currents glide eternally without losing energy, and where the tiniest motion could theoretically persist until the end of time itself. This isn't speculative science fiction, it's quantum physics pushed to its most extreme limits. What makes this phenomenon possible is the mind-bending density. Under normal conditions, even the smoothest fluids like liquid helium experience some microscopic resistance as atoms jostle against one another. But in a neutron star's core, where gravity crushes matter into a degenerate quantum soup, neutrons may pair up in such a way that they lose all individual identity, merging into a collective wave that slides without obstruction. It's akin to a Bose-Einstein condensate, that eerie state of matter where atoms chilled to near absolute zero synchronize into a single quantum entity, except here, it's happening under pressures so intense they warp the fabric of space-time. The implications are staggering. If a neutron star's core truly is superfluid, it could explain why some pulsars, spinning neutron stars that beam radiation like cosmic lighthouses, sometimes exhibit sudden speed-ups called glitches. As the star's crust spins, the frictionless superfluid beneath might lag behind, then transfer energy in abrupt bursts when the two layers briefly reconnect. Think of it like a spinning ice skater suddenly tucking their arms in, except here, the arms are an unfathomably dense quantum fluid that's been rotating at a different pace for years before snapping into sync. Superfluidity also hints at even wilder possibilities deep inside these stellar corpses. Some theories suggest protons in the core could form their own frictionless flow, creating a superconductor where electric currents never dissipate. Combined with the neutron superfluid, this would make the core a doubly exotic realm, a place where both matter and energy move without resistance, generating magnetic fields of unimaginable complexity. We're not just talking about a quirky lab experiment here. This is nature orchestrating quantum weirdness on a cosmic scale, with a star's entire mass participating in the dance. What's humbling is how these discoveries blur the line between the microscopic and the astronomical. The same quantum rules governing atoms in a lab might also steer the fate of city-sized stellar remnants, proving that the universe loves recycling its most bizarre phenomena across vastly different scales. And while we can't recreate neutron star conditions on Earth, studying their glitches and spins gives us a backdoor into physics that would otherwise remain locked forever behind the vault of extreme gravity. Neutron stars remind us that even in death, stars continue to surprise. Their cores aren't just denser than anything we know. They're teaching us that under the right conditions, matter can shed its ordinary behaviors entirely, becoming something so alien it reshapes our understanding of reality itself. HD 189733b isn't just another exoplanet, it's a horror show of cosmic extremes, where the skies rain molten glass sideways in winds faster than a speeding bullet. Clocking in at over 5,000 miles per hour, these aren't gentle breezes but supersonic hurricanes, tearing across the planet's atmosphere with enough force to strip flesh from bone in seconds. And if that weren't enough, the glass isn't falling, it's flying horizontally, pelting the planet's surface in endless, scouring waves of superheated shards. This hellish world orbits dangerously close to its host star, a searing embrace that locks one side in perpetual daylight and the other in eternal night. The temperature difference fuels those monstrous winds, as gases on the scorching day side, heated to nearly 2,000 degrees Fahrenheit, race toward the freezing night side in a violent, planet-spanning tempest. But the real nightmare is what happens to those gases along the way. Silicates in the atmosphere, vaporized by the unbearable heat, condense into tiny glass droplets as they hit cooler regions. These aren't delicate crystals, they're microscopic razors caught in the jet stream and whipped into a horizontal sandblaster that never stops. From a distance, HD 189,733b looks deceptively serene, a deep cobalt blue marble hanging in space. That striking color comes from sunlight scattering off the silicate particles in its atmosphere, a cruel irony for a world that's anything but peaceful. The same process that gives Earth's sky its blue hue plays out here, but with a lethal twist. Instead of nitrogen and oxygen, the light bounces off a haze of glass and metal, painting the planet in a beautiful, deadly glow. Strangely, this exoplanet wasn't always the monster we see today. Born as a gas giant, it likely migrated inward toward its star, where the intense radiation stripped away its outer layers, leaving behind a dense, tortured core shrouded in that infamous cobalt haze. Now, it's a cautionary tale of what happens when a world strays too close to the fire, a place where the very air is a weapon, and the only weather forecast is perpetual, violent storm. Yet for all its fury, HD 189,733b teaches us something profound about planetary diversity. It's a reminder that the universe doesn't just craft Earth-like worlds, it engineers nightmares too, pushing atmospheric physics to their most brutal limits. And as we study its extremes, we're forced to ask, if conditions like these exist, what other unimaginable environments might be lurking among the stars? If you could step back and see the universe on its grandest scale, you wouldn't find chaos, you'd see an intricate cosmic web, a sprawling tapestry of threads connecting galaxy clusters like beads on an invisible string. These filaments, stretching hundreds of millions of light years, are the universe's hidden scaffolding, woven from dark matter and ionized gas, binding everything together in a delicate balance of gravity and expansion. It's as if the cosmos itself has a nervous system, with galaxies clustering at the intersections like neurons firing signals across the void. What makes this structure even more astonishing is its sheer scale. The filaments aren't just thin tendrils, they're vast rivers of gas, hot enough to glow in X-rays, channeling material between galaxy clusters in a slow, cosmic drip. Some are so massive that if you could see them with the naked eye, they'd dwarf even the largest superclusters, threading through the darkness like highways of hydrogen and dark matter. And just like roads on Earth, these filaments dictate where growth happens. Galaxies near them grow fat on the influx of gas, while those stranded in the voids between stars left to fade into obscurity. The best analogy: picture the internet. Just as fiber optic cables link data centers, these filaments transmit the building blocks of stars and galaxies across the universe. Without them, matter would be scattered randomly, and the cosmos would lack the dense knots where galaxies congregate. But here's the twist: we can't even see most of this structure directly. Dark matter, the unseen glue holding it all together, only reveals itself through gravity, bending light and tugging on visible matter like a puppeteer hidden behind the curtain. Yet despite its invisibility, the cosmic web leaves fingerprints. Astronomers map its outline by tracking the slow drift of galaxies, or by catching the faint X-ray glow of superheated gas trapped in filamentary currents. Supercomputer simulations recreate its evolution, showing how tiny fluctuations in the early universe snowballed into this intricate lattice over billions of years. It's a fractal pattern repeating on every scale, from the branching veins of a leaf to the neuron pathways in our brain's nature's favorite blueprint, written in the fabric of space-time itself. This isn't just a pretty arrangement, it's the universe's way of organizing chaos. The web channels energy, funnels matter, and shapes the destiny of galaxies. Even now, as you watch this, filaments are collapsing under their own gravity, birthing new clusters and feeding supermassive black holes at their centers. They're the silent architects of everything we see, a reminder that even in the vast emptiness of space, nothing is ever truly alone. Mercury might be the closest planet to the Sun, but its poles hide a chilling, secret, shadowy craters where ice survives just inches away from furnace-like temperatures hot enough to melt lead. While the planet's sunlit surface roasts at 800 degrees Fahrenheit, deep within certain polar craters, pockets of water ice cling to existence in perpetual darkness, untouched by sunlight for billions of years. This isn't just a fluke of geography, it's a cosmic balancing act of extreme conditions, where Mercury's near-zero axial tilt and crater geometry conspire to create the solar system's most unexpected freezers. The magic lies in Mercury's tilt, or rather, its lack of one. Unlike Earth, which leans at 23 degrees and gives us seasons, Mercury's axis is almost perfectly upright. That means its poles barely wobble as it orbits, leaving some crater floors permanently angled away from the Sun's blistering rays. Picture a deep bowl gouged into the planet's surface, its rim towering so high that sunlight never crests over the edge. These cold traps become nature's perfect iceboxes, with temperatures plunging to negative 300 degrees Fahrenheit, cold enough to preserve ice indefinitely, even as the surrounding landscape bakes under unfiltered solar fury. But how did the ice get there in the first place? Scientists suspect comet impacts delivered it. Over billions of years, icy comets smashing into Mercury's surface would have vaporized on impact, scattering water molecules across the planet. Most would have been lost to space or broken down by solar radiation, but any molecules that drifted into these polar shadows would have frozen solid, accumulating layer by layer like frost in a freezer. Radar observations from Earth and later, NASA Messenger spacecraft confirmed the theory, detecting bright reflective patches consistent with thick ice deposits in Mercury's darkest craters. Some of these frozen reservoirs might be dozens of feet deep, a hidden water supply in one of the least hospitable places imaginable. What's even wilder is the contrast. Step just outside one of these craters and the ground is hot enough to vaporize zinc. The transition from icebox to inferno isn't gradual, it's a matter of inches, a stark line where eternal night meets unrelenting day. This duality makes Mercury a paradox, a world where fire and ice don't just coexist, they're neighbors separated only by the accident of topography. These ice deposits aren't just scientific curiosities, they're potential lifelines for future exploration. Water is precious in space, not just for drinking, but as a source of oxygen and rocket fuel. If humanity ever ventures to Mercury, these shadowed craters could offer a rare oasis in an otherwise hostile environment. They're a reminder that even in the most extreme places, the universe finds a way to preserve the ingredients for survival, hiding them in the last corners we'd think to look. Gamma-ray bursts are the universe's most violent tantrums, cosmic explosions so powerful, they outshine entire galaxies for a fleeting moment, packing more energy than our Sun will emit over its entire 10 billion-year lifespan. These aren't just bright flashes, they're the aftermath of stellar cataclysms, the death throes of massive stars or the apocalyptic collisions of neutron stars, unleashing jets of radiation so intense they can be detected from the edge of the observable universe. In seconds, a single gamma-ray burst releases as much energy as a supernova multiplied by 1,000, a shockwave of photons traveling at light speed, capable of sterilizing planets light years away if one were to hit Earth head-on. The birth of these monsters begins with two possible triggers. Hypernova, supernova on steroids, occur when a colossal star, dozens of times more massive than our Sun, exhausts its fuel and collapses not just into a neutron star, but directly into a black hole. As the star's core implodes, it launches twin jets of plasma at nearly the speed of light, piercing through the dying star's outer layers like cosmic blowtorches. These jets, focused into narrow beams by the black hole's spin, become the gamma-ray burst itself, a focused laser of destruction visible across billions of light years. Alternatively, when two neutron stars spiral into each other, their collision doesn't just produce gravitational waves, it forges a black hole in a heartbeat, surrounded by a swirling disk of superheated debris. Magnetic fields twist this chaos into jets, birthing a gamma-ray burst in a flash of ultra-dense violence. What makes these events even more staggering is their reach. In 1997, a burst dubbed JABI 970508, detected over 7 billion light-years away, briefly outshone the rest of the gamma-ray universe combined. Its afterglow, fading over weeks, revealed elements like gold and platinum forged in the neutron-rich debris, proving these explosions are cosmic alchemists, transforming simple atoms into precious metals. But there's a darker side. If a burst happened within a few thousand light-years of Earth, its radiation would strip our ozone layer, triggering mass extinctions. Evidence suggests one might have contributed to the Ordovician extinction 450 million years ago, a silent assassin from the depths of space. Yet gamma-ray bursts aren't just destroyers, they're also lighthouses. Their extreme brightness allows astronomers to probe the early universe, using them as backlights to study interstellar gas and the rate of cosmic expansion. Some bursts even serve as cosmic mile markers, their redshifts telling us how fast the universe was stretching when their light began its journey. And in their aftermath, they seed galaxies with heavy elements, scattering the ingredients for future planets and life across the cosmos. For all their fury, gamma-ray bursts are fleeting. Most last less than a minute, some mere milliseconds, but in that blink of cosmic time, they etch their presence into the fabric of space-time, reminding us that the universe doesn't just create, it does so with unimaginable violence. They're the ultimate expression of nature's power, proving that even in death, stars can scream loud enough to echo across eternity. Pluto might be a frozen dwarf planet, but its surface is anything but static here. Glaciers flow like slow-motion rivers, and towering mountains of water ice drift like alien icebergs across a frozen sea of nitrogen. This isn't the icy wasteland we once imagined. It's a dynamic, geologically active world where the very ground breathes in cycles lasting centuries. The heart-shaped Sputnik Planitia, a sprawling plain of nitrogen ice, acts as a giant conveyor belt, churning and recycling its frozen expanse in a process so strange, it defies everything we thought we knew about planetary surfaces. Imagine standing on the edge of this frozen heart. Underfoot, the nitrogen ice isn't rigid, it's viscous, creeping forward in sluggish waves under the faint warmth of Pluto's distant sun. And scattered across this slow-moving ocean are massive chunks of water ice, some as tall as skyscrapers, drifting like ships trapped in Arctic pack ice. But here's the twist: water ice on Pluto is lighter than nitrogen ice, causing these jagged mountains to float rather than sink. It's the opposite of Earth's oceans, where icebergs bob in liquid water. On Pluto, the water is the iceberg, and the sea beneath it is a thick, flowing sludge of frozen nitrogen. The real spectacle is how these icebergs move. Sputnik Planitia isn't just a flat plain. It's divided into irregular cells, each one a slow boiling pot of nitrogen convection. Heat from Pluto's interior causes the nitrogen ice to rise in some areas and sink in others, creating a cycle that drags the floating water ice mountains along for the ride. Over decades, or even centuries, these icebergs migrate, colliding, clustering, and fracturing in a silent ballet orchestrated by unseen forces beneath the ice. Scientists call these features chaos terrain, and the name fits perfectly. It's a frozen demolition derby playing out in extreme slow motion. What makes this dance even more surreal is the contrast in textures. The nitrogen glaciers are smooth and polished, sculpted by the constant churn of convection. But the water ice mountains, they're rugged and fractured, their surfaces etched by Pluto's thin atmosphere and the relentless cycle of freezing and thawing. Some of these icebergs might even be fragments of Pluto's ancient crust, ripped free and set adrift like geological ghosts from a lost era. New Horizons gave us our first glimpse of this alien landscape, revealing a world far more alive than we ever expected. Pluto's nitrogen glaciers aren't just frozen relics, they're evidence of a planet still in motion, where even at temperatures nearing negative 400 degrees Fahrenheit, the ground itself refuses to stay still. It's a reminder that the universe doesn't need warmth to create dynamism, just time, chemistry, and a touch of cosmic creativity. On the scorching exoplanet WASP 76b, the weather forecast reads like something from a cosmic horror story, molten iron rain falling from pitch-black skies. This tidally locked world orbits so close to its star that one hemisphere bakes in perpetual daylight, reaching temperatures upwards of 4,000 degrees Fahrenheit, hot enough to vaporize metals, while the eternal night side simmers at a comparably cool 2,000 degrees. The extreme temperature difference doesn't just create winds, it fuels a global maelstrom where the very air is laced with vaporized iron, condensing into liquid metal droplets that pelt the planet's dark side in an endless, hellish downpour. Picture standing on the day side of WASP 76b. The ground isn't just hot, it's glowing, a molten wasteland where rock sublimates directly into the atmosphere. Here, iron doesn't stay solid or even liquid, it becomes a gas, rising into swirling clouds of metallic vapor. But as these clouds get caught in supersonic winds racing toward the night side, something surreal happens. The temperature plummets by thousands of degrees in mere hundreds of miles, forcing the iron vapor to condense back into liquid mid-air. What follows isn't just rain, it's a tempest of liquid metal droplets, heavy and gleaming, streaking through the planet's thick, scorched atmosphere like bullets. The physics behind this metallic deluge is as fascinating as it is terrifying. On Earth, water evaporates, forms clouds, and falls as rain, a gentle cycle. WASP 76b's version turns that process into a metallurgist's nightmare. Spectroscopic observations reveal the planet's day-side spectrum brimming with iron vapor signatures, while the night side shows none proof that the iron isn't just hiding but actively migrating. It's a planet-wide distillation system where elements get vaporized on one side, transported through hurricane-force winds, and distilled back into liquid on the other. What makes this world even more extreme is its tidal lock. Like our moon to Earth, one side of WASP 76b always faces its star while the other remains in eternal shadow. This creates the most severe temperature gradient known on any exoplanet, a 4,000-degree clash between day and night that drives those punishing winds. The boundary between these two realms isn't a smooth transition either. Models suggest towering storm systems rage along the twilight zone, where superheated and freezing air masses collide, creating permanent thunderstorms that would dwarf Jupiter's great red spot in both size and violence. Yet for all its fury, WASP 76b offers scientists a rare laboratory. By studying how metals behave in such extremes, we learn not just about alien weather, but about the fundamental properties of matter under conditions impossible to replicate on Earth. This isn't just a planet, it's a crucible forging new insights into atmospheric chemistry, fluid dynamics, and the bizarre diversity of worlds beyond our solar system. And as we uncover more exoplanets like it, one truth becomes clear: the universe's imagination for crafting hostile environments far exceeds our own. Every galaxy we see spiraling star cities like our Milky Way or vast ellipticals glowing softly in the void is actually just the tip of an invisible iceberg. The real bulk of a galaxy's mass isn't in its sparkling stars or swirling dust. It's hidden in a vast, ghostly shroud called a dark matter halo, an unseen structure stretching up to 10 times farther than the galaxy's visible edge. This cosmic phantom doesn't emit, reflect, or absorb light, yet its gravitational fingerprints are everywhere. Stars on the outer fringes of galaxies rotate inexplicably fast, as if gripped by some unseen hand. Galaxies move within clusters too quickly, their visible matter insufficient to explain their speed. Even the way light bends around galaxy clusters' gravitational lensing hints at far more mass than telescopes can detect. Dark matter isn't just an add-on, it's the cosmic scaffolding holding galaxies together, the hidden puppet master shaping the universe's grand design. The hunt to unmask this elusive substance is one of astronomy's greatest challenges. Leading theories suggest dark matter could be made of WIMP, weakly interacting massive particles, hypothetical heavyweights that barely touch normal matter except through gravity. Or perhaps it's composed of actions, ultra-light particles streaming through space like an intangible breeze. Some experiments, like those deep in abandoned mines or orbiting aboard the International Space Station, search for the faintest whispers of these particles colliding with ordinary atoms. Others track gamma rays from distant galaxies, hoping to catch the telltale glow of dark matter particles annihilating each other in space. But the most tantalizing clue might be how dark matter sculpted the universe itself. Without its gravitational pull, the primordial soup of particles after the Big Bang would never have clumped together into galaxies. Computer simulations show that when you factor in dark matter's gravitational influence, virtual universes evolve structures eerily similar to our own filaments, voids, and clusters mirroring reality. Take it away and galaxies simply don't form. One of the weirdest twists, we may be swimming through dark matter right now. Billions of these invisible particles could be passing through your body every second, utterly unfelt. They don't just envelop galaxies, they permeate every inch of space, a silent ocean we're only beginning to sense. And yet, despite its dominance, dark matter outweighs visible matter 5 to 1. It remains a cosmic riddle. Is it one particle or many? Could it interact with forces we haven't discovered yet? The answers could rewrite physics itself. This invisible architecture doesn't just shape galaxies, it defines the universe's fate. Dark matter's gravity counteracts cosmic expansion, slowing the universe's stretch while dark energy fights to accelerate it. Understanding its nature could reveal whether the cosmos will end in a fiery crunch, an icy drift, or something beyond our wildest theories. For now, dark matter halos remain the universe's shadow skeletons, felt but unseen, their mysteries lingering just beyond the edge of light. Pulsars are the universe's ultimate timekeepers, cosmic lighthouses spinning at dizzying speeds, their beams of radio waves slicing through the darkness with metronomic precision. Born from the explosive deaths of massive stars, these neutron stars pack more mass than our sun into a sphere no larger than a city, their intense magnetic fields channeling radiation into narrow jets that sweep across space like a lighthouse beam. But unlike earthly lighthouses, these celestial strobes don't just guide ships, they're so regular. Their pulses rival the precision of atomic clocks, ticking off seconds with near-perfect accuracy across the vastness of space. Take the famous PSRB 1937+21, a pulsar spinning 716 times every single second. At that speed, its surface moves at roughly 1/4 the speed of light, fast enough that if it spun just a fraction quicker, centrifugal force would rip it apart. Yet despite this blistering rotation, its pulses arrive with a reliability so consistent, astronomers can predict their arrival down to the microsecond. This isn't just a curiosity, it's a tool. By tracking tiny deviations in these pulses, scientists have uncovered the faint ripples of gravitational waves, subtle distortions in space-time caused by colliding black holes or merging neutron stars as they pass through our cosmic neighborhood. The slowdown of a pulsar's spin is another treasure trove of information. Every rotation sheds a minuscule amount of energy, gradually breaking the star's spin over millennia. But sometimes that slowdown isn't smooth. Glitches, sudden, unpredictable speed-ups hint at the turbulent dynamics inside these ultra-dense objects. One prevailing theory suggests these hiccups occur when the star's rigid crust cracks under immense stress, or when the frictionless superfluid neutrons in its core suddenly couple with the crust, transferring angular momentum in a violent jerk. It's like a figure skater tucking their arms in mid-spin, except here, the skater is a city-sized ball of degenerate matter governed by quantum physics. What makes pulsars even more remarkable is their role as cosmic laboratories. The first confirmed exoplanets were discovered orbiting 1 PSRB 1257+12, a revelation that proved planets could form in the most hostile environments imaginable. Their intense gravity also serves as a testbed for Einstein's general relativity, bending spacetime so severely that light from their beams follows curved paths, creating subtle delays and distortions in their pulses. Yet for all their precision, pulsars are anything but eternal. Eventually, their spins will slow, their beams will fade, and these cosmic clocks will wind down into silence. But for now, they remain some of the universe's most reliable beacons, their rhythmic pulses not just marking time, but revealing the hidden forces shaping the cosmos. TRAPPIST-1e might be the most tantalizing world beyond our solar system, a rocky exoplanet drifting in the habitable zone of its tiny red dwarf star, where temperatures could allow liquid water to exist. But this isn't some Earth-like paradise. Tidally locked to its star, one side of TRAPPIST-1e is perpetually scorched by solar flares, while the other languishes in eternal, icy darkness. The only refuge, a razor-thin twilight strip known as the Terminator Line, where day and night collide in a precarious balance, and where life, if it exists, would cling to survival in the most extreme of Goldilocks zones. On the sunlit side, the conditions are brutal. TRAPPIST-1, the planet's host star, is a red dwarf, smaller and cooler than our Sun, but prone to violent flares that bombard nearby planets with X-rays and ultraviolet radiation. Without a protective magnetic field, the day side of TRAPPIST-1e likely has its atmosphere stripped away over time, leaving a barren, irradiated wasteland where surface temperatures soar high enough to melt lead. Meanwhile, the night side plunges into a deep freeze, with any atmosphere condensing into ice sheets thicker than Earth's polar caps. The stark contrast creates hurricane-force winds, howling from the hot side to the cold in a desperate attempt to redistribute heat, a futile struggle against the unyielding grip of tidal lock. Yet between these two extremes lies the Terminator Line, a narrow band where temperatures might hover just right for liquid water. Here, the faint warmth of the star could melt ice without boiling it away, creating a ring of potentially habitable terrain. Imagine standing on this boundary, one step forward, and you'd face the blistering glare of an endless sunrise. One step back, and you'd vanish into perpetual night. It's a world of stark divides, where life would have to adapt to perpetual twilight, relying on chemosynthesis or the dim, ruddy light filtering through the thick, turbulent atmosphere. But the Terminator Line isn't just a static border, it's dynamic. Seasonal shifts in the star's activity, or even geothermal heat from the planet's interior, could create pockets of stability. Subsurface oceans might lurk beneath the ice, shielded from the deadly radiation above. Some models suggest that atmospheric circulation could carry moisture from the night side to the Terminator, where it condenses into frost or even flows as transient streams. If life exists here, it wouldn't look like anything we know, perhaps clinging to rocky outcrops in the dim light, or thriving in underground aquifers warmed by geothermal vents. TRAPPIST-1e forces us to rethink the very definition of habitability. It's not just about distance from a star. It's about how a planet negotiates the violent whims of its host, the resilience of its atmosphere, and the ingenuity of any life that dares to emerge in such a fractured world. As we scan the cosmos for signs of life, this tidally locked enigma stands as a reminder. The universe doesn't care about our expectations. It crafts its own rules, and sometimes the most promising worlds are also the most alien. Somewhere beyond the Milky Way's star-dusted veil, an invisible force tugs at our galaxy and everything around us with irresistible gravitational might. This is the Great Attractor, a cosmic anomaly so massive that it warps the very fabric of space-time, dragging entire galaxies toward it at millions of miles per hour. Hidden behind the thick band of stars, gas, and dust that marks our galaxy's plane, this gravitational behemoth has remained one of astronomy's most perplexing enigmas, its true nature obscured by the Milky Way's own celestial clutter. For decades, astronomers puzzled over why thousands of galaxies, including our own, seemed to be racing toward a single point in the constellation Centaurus. Measurements revealed an unexplained bulk flow, a vast river of galaxies all moving in unison, as if pulled by something colossal lurking just out of sight. The culprit, a concentration of mass so dense it defies conventional explanation, with a gravitational pull of roughly 100 quadrillion suns. Yet because it lies directly behind our galaxy's central bulge, optical telescopes could barely glimpse its influence, leaving scientists to map its presence indirectly through the motion of galaxies caught in its grip. Recent breakthroughs have peeled back some of the mystery. The Great Attractor isn't a single monstrous object, but the heart of the Laniakea supercluster, an immense web of galaxies spanning 500 million light-years, with our Milky Way residing on its distant outskirts. Picture Laniakea as a cosmic watershed, where galaxies flow like rivers toward the gravitational basin of the Great Attractor, much like water draining into a valley. At the center of this basin lies the Norma cluster, a dense knot of galaxies and dark matter whose combined gravity orchestrates this grand celestial motion. What makes this discovery even more astonishing is the scale of our place within it. The Great Attractor isn't the end of the journey, it's merely a waypoint in an even larger cosmic migration. Beyond Laniakea, an even greater force calls the Shapley supercluster, a staggering assembly of galaxies over 600 million light-years away, whose gravity tugs on the Great Attractor itself. This hierarchy of pulls Milky Way toward the Great Attractor toward Shapley reveals the universe's fractal-like structure, where clusters nest within superclusters, all caught in an eternal dance dictated by dark matter's unseen hand. Yet the Great Attractor's secrets aren't fully unraveled. Why is there so much mass concentrated in this region? Could there be exotic structures, cosmic filaments, or dark matter halos amplifying its pull? And what lies beyond Shapley steering this chain of motion? Each answer peels back another layer, reminding us that even as we map the cosmos, the universe reserves its grandest mysteries for those who dare to look deeper. Uranus and Neptune aren't just ice giants, they're cosmic treasure vaults, hiding layers of glittering diamonds deep beneath their swirling blue atmospheres. While their surfaces rage with winds faster than a jet engine, their interiors could harbor something even more extraordinary, a thick mantle of crystallized carbon, forged under pressures so intense they turn methane into diamond raindrops that never stop falling. This isn't planetary science fiction, it's the likely fate of carbon atoms crushed under the weight of 60,000 Earth atmospheres, where the familiar rules of chemistry twist into something unrecognizable. Lab experiments here on Earth have recreated these extreme conditions, zapping hydrocarbons with high-powered lasers to simulate the crushing depths of these distant worlds. In nanoseconds, the carbon atoms rearrange themselves into crystalline structures, actual diamonds forming right before researchers' eyes. But on Uranus and Neptune, this process isn't a fleeting lab curiosity, it's a planetary-scale phenomenon happening continuously across layers hundreds of miles thick. Picture an ocean of liquid diamond, not solid like Earth's gemstones, but a strange, electrically conductive fluid that might even generate these planets' lopsided magnetic fields. The journey from methane clouds to diamond core begins in the upper atmospheres, where lightning storms and extreme pressure rip apart methane molecules, freeing carbon atoms to sink deeper. As they descend through layers of supercritical water and ammonia, the pressure mounts until around 5,000 miles down carbon crystallizes into diamonds. These aren't tiny specks. Some could grow as large as icebergs, slowly sinking toward the core in a process scientists call diamond rain. Over billions of years, this glittering precipitation might have accumulated into a thick diamond layer above the planet's rocky hearts. Even more fascinating, these diamonds might not stay solid. At the boundary between the diamond layer and the rocky core, temperatures could reach several thousand degrees hot enough to melt the diamonds into a liquid sea. Unlike Earth's oceans, this wouldn't be water but an exotic, metallic fluid capable of conducting electricity, possibly explaining why Neptune's magnetic field is so chaotically tilted. The diamonds themselves might even interact with silicate minerals in bizarre ways, creating hybrid compounds that don't exist anywhere else in the solar system. What makes this discovery revolutionary isn't just the bling factor, it's how these experiments reshape our understanding of planetary interiors. If diamond formation is this common under high-pressure conditions, it could occur in gas giants across the universe, rewriting the chemistry of how we model distant exoplanets. Uranus and Neptune, long overshadowed by their flashier gas giant cousins, might hold the key to understanding a fundamental planetary process happening throughout the cosmos. And while Neptune's winds howl at 1,300 miles per hour and Uranus rolls sideways through space, deep below their turbulent surfaces, the real magic happens in the dark, where carbon becomes crystal, and the universe proves once again that its imagination dwarfs our own. The Boötes void is less a place in space and more a cosmic anomaly, a gaping absence so vast it defies comprehension. Stretching 330 million light-years across, this spherical desert contains almost nothing, no galaxies, no stars, just an eerie silence where the universe's usual cacophony of light and matter simply vanishes. To put that in perspective, if the Milky Way were a grain of sand, the Boötes void would be an empty sphere larger than Earth itself. This isn't just a quiet neighborhood, it's a hole punched through the cosmic web, a blank spot on the map so unnerving that astronomers first dismissed it as an observational error. What makes this void truly bizarre is how it clashes with our understanding of the universe's structure. The cosmic web, the sprawling network of galaxies bound by dark matter filaments, should distribute matter relatively evenly like froth on a latte. Yet here, in the heart of Boötes, the froth disappears, leaving a bubble of near-nothingness. Only 60-odd galaxies have been found in this colossal expanse. Statistically, there should be thousands. It's as if someone took a cosmic eraser and scrubbed away everything but a handful of survivors. The few galaxies that do cling to existence here are isolated, stranded like lone outposts in an ocean of darkness. Theories about the void's origin range from the plausible to the mind-bending. One idea suggests it's the aftermath of a collision between universes in the multiverse, an imprint left by a sibling cosmos brushing against our own. Others propose it's the work of ancient quasars or supermassive black holes whose energy cleared the void like a snowplow pushing matter to the edges. Then there's the unsettling possibility that the Boötes void isn't empty at all, just filled with something invisible, like dark energy manifesting in ways we can't yet measure. But perhaps the most humbling takeaway is what the void implies about our place in the cosmos. For all our maps and models, the universe still holds regions that shouldn't exist, or at least shouldn't exist this way. The Boötes void forces us to question whether our cosmological theories are incomplete, missing some fundamental force or phenomenon that carved these unnatural vacancies. And if one such void exists, how many others lurk beyond our sight, waiting to rewrite the rules we thought we knew, standing at the edge of this abyss, figuratively, of course, is like staring into the universe's blind spot. It's a reminder that for all its splendor, the cosmos reserves pockets of mystery so profound, they don't just challenge our understanding, they dare us to imagine entirely new ones. From the unimaginable density of neutron stars, where a teaspoon of material outweighs mountains, to the haunting emptiness of the Boötes void, a cosmic desert so vast it could swallow galaxies whole, we've journeyed through the universe's most extreme frontiers. We've witnessed diamond rains on distant ice giants, wandered tidally locked exoplanets where metal falls like hail, and stood at the precipice of black holes where space-time itself unravels. These aren't just abstract curiosities, they're nature's way of flexing its creative muscles, proving that reality can outshine even the wildest science fiction. What makes these extremes so thrilling isn't just their sheer spectacle, it's how they force us to rethink the rules. Every time we encounter a magnetar's lethal magnetism or a rogue planet's frozen abyss, we're reminded that the universe operates on a scale beyond human intuition. Our everyday experiences gravity as a gentle tether, temperature as a manageable range crumble in the face of environments where atoms are crushed into oblivion or where time slows to a crawl. These phenomena don't just defy expectations, they rewrite the textbooks, challenging scientists to invent new physics just to make sense of them. Yet for all their violence and strangeness, these extremes are more than cosmic freak shows. They're keys to understanding how galaxies form, how matter behaves under unfathomable pressure, and even how life might arise in the unlikeliest corners of the cosmos. The same crushing forces that birth neutron stars also forge the heavy elements in our bones. The same void that unnerves us with its emptiness might hold secrets about dark energy's grip on the universe. Every extreme is a puzzle piece waiting to slot into the grander picture, and here's the most exhilarating part: we've barely scratched the surface. For every quasar we've mapped, there's a deeper mystery lurking in the shadows. For every exoplanet we've catalogued, there are billions more, each with its own bizarre story. The universe doesn't just tolerate extremes, it thrives on them, crafting new wonders faster than we can discover them. So stay curious, keep looking up. Because out there, in the uncharted vastness, the next mind-bending revelation is waiting, and it's bound to be stranger than anything we've dreamed up so far.